Guys, so my objective tonight is to try to accomplish three things. Thing number one is to introduce the concept of correlation and regression. Okay, the regression word's a little weird, but you'll understand what it's supposed to mean once we get a chance to look at it a little bit more closely. That's thing number one. That's a new topic. We haven't talked about it before. It's another analysis that we can use. So far, we have analyses that we can use to look for an association between the means of two groups. For instance, we use a t-test to compare, say, males to females, Americans to Europeans, in terms of a numerical variable, like weight, BMI, blood pressure, and so on and so forth. So we have two variables we're working with there when we use the t-test. We're working with a nominal or categorical variable like gender, and we're working with a numerical variable like blood pressure. Nominal and numerical, in other words, categorical and numerical, whichever way you want to term it. In fact, SPSS calls numerical variables scalar variables. Okay, so that we use a t-test for. We use t-test for when we're comparing only two values in that categorical variable, male or female, diabetes or doesn't have diabetes. Premature, not premature, right? Only two variables in the categorical variable. Because you use a t-test to compare the means of two groups, right? So now what do we do if we want to compare the means of more than two groups? So for instance, we want to compare the ethnicities of a population by ethnicity. So ethnicity could have 3, 4, 5, 10, 20 ethnicities, right? If you broke it down completely enough. So how do you compare the ethnicity of 7 different groups in terms of their average BMI, for instance? How do you compare those? Because you are looking at means. Is the mean BMI for this group different from the mean BMI for group B and group C and group D and so on and so forth? You could use a t-test, right? Compare group A to group B, then compare group A to group C, group A to group D, and so on and so forth, going all the way through them. And then you'd have to go back and compare group B to C, and B to D, and C to D, and so on and so forth. So it's just like a regular permutation of number of times you'd have to do that. T-test isn't really designed to do that. Each time you run the t-test, if you run it at a significance level, an alpha of 0.05, it's 5% chance of being wrong. If you do it over and over again, you will increase your probability of rejecting the null hypothesis when you shouldn't be rejecting the null hypothesis, which is the bad kind, type A or type 1 error that we're talking about. So we don't want to use the t-test. So we use a different test called analysis of variance. And they call it analysis of variance because the way it distinguishes, it sounds like it's talking about variance instead of means, but it is a way of comparing means of many different groups at the same time. And the way that it does that is that it looks for the mean of each group and the variability of each group, right? So ideally, you use analysis of variance to prove that means are different from one another for different groups. And it's easiest when the means for each group are far apart, right? Makes sense, right? Because it's easy to tell that the means are different. Further apart they are, the more likely is that your sample result is really how the mean would be for the population. And the other thing that helps your analysis of variance is when the variability within the groups is very narrow. In other words, you want a narrow variability within the groups so they're tightly packed together, and you want a wide variability between the groups. And you combine those two in a fraction, in a ratio that we call the F-score, right? The F value, right? The F statistic. And you can use analysis of variance to tell you what the probability is that at least 2 of those means are different from one another. So where our null hypothesis for the t-test look like the mean for group 1 is equal to the mean for group 2, and the alternative mean for group 1 does not equal the mean for group 2. Now for analysis variance, we can say mean for group 1 is equal to mean for group 2 is equal to mean for group 3 is equal to mean for group 4 is equal to mean for group 5, and so on. And then anybody want to hazard a guess what our alternative hypothesis would be? At least 2 of the means are different. Not all of the means, right? Analysis variance only tells you that at least 2 of those comparisons are different. If you don't get a result, the significance of less than 0.05, when you do analysis of variance, when you calculate that F-score, you're done. You can't, statistically, you cannot prove that any of the means are different. So you fail to reject that null hypothesis that they're all equal. Doesn't mean they're all equal, just means you can't reject it, right? So, well, what does it mean when you do get a result less than 0.05 for the probability? What that means, at least two of those are different. Now, the problem is that, yeah, you now need to figure out which of the two are different. So once you've completed the analysis of variance and you're satisfied that at least two of the means are different, you can do something called a post hoc test. That post hoc test is built into SPSS. There's many different forms of it. The most common ones are Bonferroni, and there's a couple others as well. Each one of them takes a different approach to looking at that result for analysis of variance to try and identify which means are really actually different from one another. Okay, so those are called post hoc tests. Post hoc means after the fact. That means you only run them after you've proved, or after you prove to the level of certainty that we accept, which is 5% chance, less than 5% chance of being wrong, that you can reject the null hypothesis. Then you can run the post hoc tests, right? How many of you guys watched the video from last week? Okay, not everybody, but quite a few of you guys. Okay, did you guys run out and go to the botanical gardens right after? Okay. I think it was a little late, right? What's that?
I actually, like, when I went to the pond, I actually tried to see if, like.
Oh, Brooklyn Botanic. That's a Brooklyn Botanic. Oh, yeah, there should be some cherry blossoms. They're probably gone now, so a little bit later now. So at any rate, yes?
When you later say, you say that the two means are different, you have three different means, but can you visually go back and say that this is the highest, this is the lowest?
You could say, remember, we've been staying away from this. I want to stand back here so it records my voice. We've been staying away from one-sided hypothesis, right? Where we're hypothesizing that this mean is less than this one. And we've been sticking with that the means are different, right? So, it is pretty obvious that if you demonstrated with less than 5% chance of being wrong, that these two means are different, well, then, yeah, you can probably make the assumption that the means of that suggests that the means of the population with the sample with the lower mean is also lower than the population with the higher mean. So, yeah, you can kind of do that, I would think. Right, but that's not really what we're doing here. We're doing a two-sided test. We're not concerned at the moment about which is bigger or smaller. It's just that they're different. So you can reject the null hypothesis that they're different, and then we can go on and worry about that later on. So, but yeah, you can kind of draw that conclusion that if they're different, and the sample mean for this one is lower than sample mean for that one, for group B, let's say, or group C, then you can presume that that would suggest that the population mean for group A is smaller than the population mean for group C, or blood pressure for people taking the drug drug A is lower than it is for people taking drug D, for instance. So yeah, I think you can make that leap, or at least that's kind of what you would be looking for anyway. But as far as the test is concerned, the test is just looking for a difference. It doesn't care which one's bigger or which one's smaller in the test. You then can go back and look at the data and make your own conclusions about that. So I'm going to run one of these just to make sure everybody who's seen this done is comfortable with it. We have most of our data in the databases that you have is categorical data, like the community health survey, diabetes, yes or no, influenza vaccine, yes or no, insurance, yes or no, Burroughs categorical data, except it's 5 categories, right? So on and so forth. There are some numerical variables in that data set, for instance, age, I think number of cigarettes smoked or something like that. But there is some numerical variables in there which they even calculate means, use the t-test, use analysis of variance, but most of it is categorical variables. So that's how we would deal with looking at the means of several different groups at the same time, analysis of variance. I'm going to demonstrate in a moment. The next test that we're interested in is, well, what about categorical variables? What can we do with them? Okay. In other words, for instance, if we wanted to know whether people who are diabetics were more likely to get an insulin visit, that might be that data. If that data is not in the reduced data set, it's going to be in the full data set, right? Do we want to let's try and decide whether people who've been told they've been a diabetic in the past year are more likely to get a flu vaccine or less likely to get it, or not, as no difference in whether or not they would get it. So what's the variable? Diabetic, yes or no, categorical variable, 2 values, and got a flu vaccine or didn't get a flu vaccine, 2 values for a categorical variable. So that makes a 2x2 table, right? Diabetic, not diabetic, and columns would be got the flu shot, didn't get the flu shot. What test do we use when we want to determine whether there's an association between diabetes and getting the flu shot? Right, chi-square, exactly, right? Anytime we have categories, 2 categorical variables, we would do that. If we wanted to know is there an association between the borough you live in and whether or not you got an influenza vaccine, right? Well, that's now 5 values. So for instance, that might be 5 rows and 2 columns. We can use chi-square for that also. Chi-square will work for any number of columns and rows. So we might see, so what would our null hypothesis be there? Null hypothesis there is a little bit different. We would probably say null hypothesis is there's no association between being diabetic and whether or not you're likely to get a flu shot. Alternative hypothesis, there is an association, right? For borough, there's no association between what borough you live in and whether or not you have a flu shot, right? Or if we got enough evidence from chi-square to reject the null hypothesis, then we could say there isn't we can reject that there is no association and conclude that there is an association. So now the 2x2 table that I mentioned, diabetes and flu shot or no flu shot, that is a little bit of an advantage being a 2x2 table. Why is that? What else can we do with a 2x2 table we can't do with a 2x5 table? We can do the odds ratio and relative risk. We can calculate that as well. And that's a handy function, right? Relative risk odds ratio is nice because you can say, when you can do an odds ratio, you can say that the odds that you would get a flu shot if you were diabetic are 1.3 times as great, as if you weren't diabetic. Or if you lived in Brooklyn, you were twice as likely to get a flu shot than if you lived in any of the other 4 boroughs. If you combine all those 4 boroughs into one variable, right? There's ways we can change the data set from more than a 2x2 table into a 2x2 table. So I'm going to demonstrate that. At the last hour, I'm going to spend working on ways that you might attack the data in these different data sets to help you prep for next week, to help you wrap your heads around what we're doing next week. I'm going to set up like sometime on Sunday, an hour or 2 where I'll just sit in front of the computer online. And if you're having difficulty, you can get online live with me and maybe, like help you out a little bit on the project. So you get a little bit more insight. You might be able to do a Monday night too. I'm not sure about Monday night. Okay, so at any rate, so that's that test. So what's missing now? Categorical, numerical. What about numerical? What if we want to see if there's an association between a person's BMI and their blood pressure? They're both numerical variables, right? So I can't say, BMI is all different numbers. So there's no group in there. I can't compare. I could maybe say, let me group these all into high BMI and low BMI or something like that, call it a category and do a t-test, right? But if I want to use the raw data, the numbers, well, I need another test for that. That's where correlation and regression comes in. Okay, so a couple of you guys, when you sent me emails or something like that, or sent me some notes on what you plan on doing, you had mentioned that, let's look for a correlation between premature and not premature and something like this. And I probably corrected you and said, do me a favor, don't use the word correlation for that. Use the word association or something similar, because correlation in statistics means something very specific. And I'm going to show you what it means right now. Okay, so let's start with correlation and then and regression, and then we'll spend about an hour on that. Take a quick break. We'll have a little presentation, and then we'll come back and we'll pick up with these other tests, how we interpret them, and then finally with some help on the project. Okay, so let me get started on this. Is that working there, by the way? Yes, it is. I'm waiting for that to start up. No. Okay, this is on Blackboard, as are the data sets that go with this. There's two data sets. One is called, they're both called age versus blood sugar. One of them is an Excel file, and the other one is an SPSS file. Okay. Okay, so I want to start with just this idea of what does correlation mean. I'm going to draw a chart here. Nope, we don't want to do that. I want to get this out of the way. Okay. I'm going to start with a graph, two axes, X and Y axis. Oops, oops. Yep, come on. Okay, here's our X and Y axis. And I'm going to start this in 1960, and 1970, 1980, 1990. Actually, I don't want to do that. Let me start again. Kind of got my own way there. Okay, so I'm going to start down here at 0.1, 0.2, 0.1, 2.5, 1.0, 2, 3. Little awkward doing this here. Okay, now on this bottom axis, and up here I'm going to do the same thing. 0.1. I'd say this is $1. This is $2. This is $3. Okay, in 1960 or so, when I was a little kid, and if I wanted to go over and take the subway, I would pay 15 cents for a token, a little tiny token, smaller than a dime, right? I pay 15 cents. If I took that subway ride to the local pizza store, a slice of pizza would cost 15 cents at the same time, right? So if I went here, I'm gonna call this the price of pizza. I'm gonna call this axis the cost of a subway ride. Okay, so let's see, 15 cents is here, and 15 cents for the pizza is around here somewhere. So that point right there would be the point 0.15 on the x-axis, and 0.15 on the y-axis. Right? Now, fast forward to 1970, let's say. 1970, price on Subway goes up to 25 cents. And now we're at 25 cents. Price of pizza goes up to about 25 cents. Right? 1980, price of Subway goes up to about 75 cents. And the price of pizza, let's say, goes up to $1. And 1990, price of a Subway ride now is about $1.50, and the price of pizza is, let's say, $1.90. 2000, now the price of a Subway ride is $2, and a slice of pizza is about, say, $2.25. Okay, now we go to today. Today, Subway ride is $2.75. I guess if you just do a single fare, right, it's $2.75. And a slice of pizza, of course, a slice of pizza is maybe about $2.50. What do you notice about those values? As one goes up, the other one goes up. That's what we refer to as a correlation. It's an association where which one changes, the other changes along with it, right? So if I wanted to, I could kind of draw a line between these. Actually, that's not a great line because it's below all of the values. I could draw a line that approximates, come on, disappear. Not let me do it. I could draw a line that approximates that slope, that increase, that change in the price of pizza versus change in the price of the Subway. That slope gives us an idea about how fast they're going up and how strong the association is. So I could have a situation where the price down here was 15 cents and the price of pizza was $2, and then here was that, and then that, and then that, and so on and so forth. And that line would look something like this, right? And that's not as strong an association, right? It's not all falling so closely to that straight line. That straight line is basically a best fit straight line for approximating all of these different values. And basically what it's doing is it's taking the distance from each one of these points and squaring it, and then adding it to that one, and then taking this one, adding all the ones on this side, and it's trying to balance it so that all of those differences are the same. That's really what that line is doing. Okay? We're going to take advantage of that calculation to create a statistic called correlation, which is going to tell us how closely these two values are associated. As one goes up, the other goes down, and whether or not it's a statistically significant association. Well, why is that so important? Well, you know, if you want to know if there's an association between a certain hormone and some weight gain, for instance, that would be interesting to see as the hormone increases, whether weight gain increases and so on. If there's hair loss as you from higher levels of testosterone, right? Maybe the amount of hair loss goes up as the level of testosterone goes up. I don't know how you do that. Maybe count hairs or something like that. Pull hairs off the brush or something. But you get the idea. Two numerical variables. So we're going to examine one of those situations. The one we're going to examine is the idea that there's no association between age and blood sugar. We have a random sample of 10 individuals, different ages. We measure their blood sugar. Obviously, this is kind of, fake data and stuff, right? We measure their blood sugar, and we want to see is there an association between these two values. If I were to look at the Excel file, this is what it would look like. There we go. Okay. This is a new version of Excel, so it's going to take me forever to figure out how to get it to increase in size. Here we go. Okay. Here's blood sugar, here's age of blood sugar, and so on. They're just side by side in two columns, right? In fact, I know I can import this data from Excel into SPSS. I'm going to close this for a moment. I also have an SPSS version of this file here as well. But just to show you how to import it into SPSS, I'm going to open SPSS first. Okay. Okay, here we go. I'm going to get this out of the way. Here's my blank data sheet in SPSS. I'm going to go to File, say Open, Data, and I'm going to navigate to the desktop. Okay, here's the desktop, and I'm going to look for what files I have outside of my folders here. That I don't think I went into the desktop. There we go. Okay, notice that there is a file there, age versus blood sugar, .sav. That's showing up right now because that's an SPSS file. .sav, that's an. I could open that right now. Just double click on it or say choose and so on and so forth. I could open that right now, but I want to demonstrate importing the data from Excel. And in order to do that, it has to be able to see the Excel file. So right now, all it can see is the .sav file. So I click down here and I tell it, look for Excel files on my desktop. And now you can see several Excel files, including, let's see, here's the blood age versus blood sugar Excel file. Okay, I can click on that, double click on it, or just click open. And SPSS will recognize that it's an Excel file. It'll import it, but first it's going to ask me if it's the right file. And it notices that there's data between A1 and B12. And let's see, okay. Well, you know, there must have been a blank space in number 11, right? So I can actually tell it that I only wanted to, actually, I'm going to import the blank space. I'll get rid of it later. Okay. I do have to tell it that, gee, you know, that that top line is the variable name, age and blood sugar. If this is not checked, read variable name from top line, it'll think it's data. So now you can see that it's including those words in there as data. I don't want that. I wanted to know that those are the date names of the data. So don't include them and start with the second row as far as the data is concerned. And once I'm satisfied, I can click OK. And SPSS will import it and create a SPSS file. And there it is, imported into SPSS. I could have got to the same spot just by opening the SPSS file, the .sav file. So here's my data. I can't blow this up, unfortunately, but because SPSS is not cooperative that way. So let's take a look at what I can do now. So now I want to evaluate this data to see if there's an association between age and blood sugar. When I was curious about looking for an association between pizza and the price of a subway ride, did I go immediately to a statistical test? No, what did I do first? I drew a graph to see if it looked like there was an association. I'm going to do the same thing here. I'm going to go up to graphs. I like to use legacy dialogues. There's also a chart builder. There's all sorts of aids and stuff like that, but I'm old. I'm in legacy, so I like using legacy. I go into scatter dot, and I want a simple scatter dot. Scatter dot is when you take each pair of points and put them on a graph as an XY coordinate, right? For each person, their weight and their blood sugar are an X and a Y coordinate. So I'm going to click define, and I'm going to tell it that the x-axis is age and the y-axis is blood sugar. When we're dealing with correlation, which one we put in the x-axis and the y-axis doesn't matter, because we're only looking for an association. We're not looking for causality, right? Correlation has nothing to do with causality. For instance, if I told you that there's an association, a correlation between the amount of damage done in fires, house fires, and the number of firemen that show up. Would that make sense to you? Yeah, right, makes sense. Because bigger fire, more firemen, right? More damage, right? Are the firemen causing the damage? No, it's the fire causing the whole, yeah, sometimes. Occasionally, I've seen, I have friends that are firemen, so I know how they can be a little rambunctious. But in general, it's the fires causing the damage. There's a definite association. There's a real correlation there. You have bigger fire, you're going to have more damage. You're going to have more firemen at that fire, right? So there is a correlation, a real correlation, but there's no causality. So in correlation, we're not interested in causality. We're not using it to demonstrate causality. just to demonstrate an association. When we get to regression, we're going to start talking about causality. Okay, so I'm going to put this in here. Age is the x-axis, and blood sugar is the y-axis. I'm going to click OK, and I'm going to get a graph. And here is my graph. Okay, can you see those points up there? Okay, so does it look like there's an association? Right? As age goes up, we have more points that are higher for age. I can actually get SPSS. I can double click into this graph and ask SPSS to put a best fit line in there. Let's see, add a fit line in total. That's the one we want. And it will add a line there. And that's that best fit line I told you, where it kind of trades off the points above and the points below and gets the line that represents the best fit. Okay, now what else do we notice about this? It does look like there's an association, a correlation between these, and which makes sense, biologically, let's say, right? But I also noticed that as age goes up, what happens to blood sugar? Goes up also, right? Okay, that's a positive correlation. Well, how about if I asked you, let's see, we compared age and let's say weightlifting ability, maximum weightlifting ability, right? So what's going to happen with that? As age goes up, weightlifting ability goes down, right? So that would be a negative correlation, right? So we're going to, SPSS has a statistic in here called the R statistic, or rho or R statistic, and it's called Pearson's correlation coefficient. We're going to calculate it right now. Analyze, descriptive, let's see, where are we? Correlation bivariate. Why is it bivariate? We have two variables. For our purpose, we're only going to work with two variables right now. Okay, so I'm going to put age and blood sugar in here for the variables. Notice it doesn't care which one I put in first. Just wants me to move over into a box. And I'm going to calculate this Pearson's correlation coefficient. I'm going to click OK. And here's our calculation. Okay, so what is the Pearson's correlation coefficient? Pearson's correlation coefficient can have a value from -1 to +1. A perfect correlation. If all those points line up and all of them lay right on that straight line, in other words, you can absolutely with that line predict what another value might be. If they're all flat on that straight line, that's a perfect correlation, perfect association. That's a correlation coefficient of +1 or -1. So the closer it is to +1, the closer it is to -1, the tighter the association between those two numerical variables. Right? Knowing that, if you're not close to 1, if you're close to 0, what does that imply? There's no association. Imagine a flat line like this, no slope at all, a flat line like this. If every one of those dots landed on that flat line, would that mean that it's a good correlation? No, because it would mean that for every value that this is, the other is always the same value, right? So there's no association there at all. So we're looking for the slope up or down to tell us whether it's a positive correlation or a negative correlation. The sign on Pearson's correlation coefficient tells us that as well. And the size of the correlation coefficient, -1 to +1. The closer it is to -1 to +1, the stronger the correlation. So let's see what we got. We got a correlation of 0.821. That's actually a pretty good correlation, right? And what would our null hypothesis be here? Our null hypothesis would be that there's no correlation between the age and blood sugar, right? Or another way of saying it would be that R, rho, is equal to 0, right? In other words, no correlation. And our alternative hypothesis would be that there is a correlation between age and blood sugar. Another way to say this, rho R is not equal to 0, right? There is some association between them. In fact, in this case, it's a nice correlation. So is there a p-value or probability associated with this? And in fact, there is. If you look here, the significance is 0.004. That's our p-value. In order to reject the null hypothesis that rho is equal to 0, what do we want that number to be less than? Let it be less than 0.05, exactly. So it is less than 0.05, so we can reject our null hypothesis. Okay, so we've demonstrated that with a certain level of certainty, right? In statistics, we're never absolutely certain, but with a level of certainty that satisfies us, that there's an association, a correlation between these two numerical variables. Okay, let's take that a step further now. Let's say that age does cause blood sugar to go up. Wouldn't it be really useful to be able to say, gee, let's see how much of an impact age has numerically. Can I predict the person's blood sugar from their age? That's where regression comes in. Okay, so in regression, we're going to take this same information and we're going to analyze it to see if we can demonstrate an association that we can represent as a line that will help us predict how strong this association is. Okay, so let me get that. Okay, no, I don't want that. Okay, so let's go up here, analyze. I'm going to go down here. Right after correlate is regression, right? Now, we're working with regression, a lot of different kinds of regression. We're working with linear, simple linear regression right now. So I'm going to go over to this selection over here, linear. Correlation, bivariate, regression, linear. So I'm going to go in here. And again, this is something you can do if you happen to have numerical data you want to work with, you can do this. Okay, so what is our independent variable? The independent variable is the one that's going to cause the other to change. So I don't think blood sugar is going to make age, right? So I'm going to say that our independent variable is age. Oops, come on. And our dependent variable is blood sugar. So now I can get it to plot it for me and so on and so forth. But I'm just going to ask it to calculate the correlation coefficient. I think it's going to do it for me anyway. Okay, let's do that. And here we go. Well, the first thing that it does is it calculates the correlation coefficient. Again, 0.821, which is what we got before, right? Okay, there's a correlation coefficient. Then it also calculates something called R squared. The correlation coefficient, rho or R, it takes it and squares it. Like 0.821 squared is 0.674. That number is going to be valuable to us in a second. Then it looks for the variability of the different of the values, how different they are, and it attempts to tell us what the probability that this is a real association. That's where that 0.004 came from when we did rho. So this is a significant association. We can reject the null hypothesis. There is an association. And then it gives us an extra table at the bottom down there called coefficients. So what is it doing when it gives us a coefficients table? I'm going to go back to my little chart there, and I'm going to drag you guys back to algebra. When's the last time you took an algebra class? Been a while, right? Okay. So now, if I draw a line straight, if I draw a graph, right, I draw this line, right? The formula in mathematics, in algebra, usually you see the formula is y is equal to mx plus b. This is the x-axis, this is the y-axis. Y is equal to mx plus b. Okay, so in statistics, you usually see it as y or f of x is equal to, I think it's beta x plus alpha. Is that it? Is that the way it looks in your text? That's pretty much it. It's basically the same thing, except beta here, M and beta the same thing, and B and alpha the same thing here. What does this formula mean, right? What is the beta and what does the M represent? Anybody remember the formula for a straight line? What does that number in front of the X represent? It hasn't been that long, right? That's the slope of the line. Okay, somebody took algebra last week, and they remember. That's the slope of the line. How do you get that? Well, you get that by looking at the change in X, the change in Y, over the change in x, right? That's the difference between those two. So the slope, if this is 1 and this is 2, the slope of this line would be 1/2. And if the line were going this way, right, the slope might be minus 1/2. If it's a really sharp slope like this, right, the slope might be 3. For every 1 you go x, it goes up 3 in the y direction. Right? So that tells us the slope of that line. Okay, what about this other number, b, or alpha, over here? What does that b represent? That b represents, well, what happens when x is 0? When x is 0, right, when x is 0, y is equal to that number. When is x 0? X is 0 here, right, at the axis where it crosses the y-axis, right? So this number b represents where it crosses the y-axis. That's called the y-intercept. Okay, let me just draw this another way. Okay, I'm going to say that this value is 5, and this line, the slope of this line, m, is equal to 2. Okay. So with those two things, knowing the slope of the line and one point that it passes through, we can draw that line. We know that line perfectly, right? That'll tell us that this line is y is equal to 2x plus 5. So I can find that line, the value of that line for any value of x. X is 10. This would be 10 times 2 is 20 plus 5. This would be a y value of 25. That would be 20, 25, right? All we need to know a line perfectly, a formula for a line perfectly, is the slope and the y-intercept. Well, let's go back to SPSS. So what is y, what in this coefficients, what does y give us? It gives us, unstandardized coefficient, it gives us something called a constant, and it gives us age, a value for age. That constant represents the y-axis, the y-intercept. And this value, this b value for age, represents the slope of that line, right? So if I were to go back here again, and I were going to try another blank piece of paper here. Okay, and I'm going to draw this. Okay, and let's say the y-intercept is about here, and the slope looks something like this. Okay, and this is age, and this is blood sugar, right? This would be 17, right? And the slope of this line would be y is equal to 1 point, I forget what it was, 1.76 plus 17. Okay. That's our formula for that line. So now, this is x. In our case, y represents blood sugar. Blood sugar is equal to 1.76 times a person's age plus 17. Okay. So now, what does that mean to us? That means that if I want to predict a person's average blood pressure, likely blood pressure, I can just fill in his age here. Let's say his age is 30 years old. That's 1.76 times 30 plus 17. What do I get? Plus 17. So I would predict that his blood sugar is going to be about 70. This is kind of a hokey example here, but there are a lot of applications where this may have some value. So if you have a test that's easy to perform, medical test that's easy to perform, and it has, and you can prove there's an association between the value you would get with that test and a more expensive and more difficult diagnostic test, then you could just simply rely on the simpler test as a diagnostic tool rather than the more expensive one. Right? So there's a lot of reasons why this might be of value to you. Another reason why it might be of value to you is that, let's say, for instance, if we were looking at, let's see, staffing, nursing staffing, okay, versus, like in other words, say, number of nurses per patient for different hospitals, and mortality rates. Right, so you got each point represented the number of nurses per number of patients per nurse, 20, and mortality rate was let's say 10 per 1,000 or something like that in some sort of hospital. And then if the staffing went up, perhaps the mortality rate went down further, and so on and so forth. That slope would tell you how increasing staffing will affect mortality rates. So that's something that you could use to determine whether or not your budget for your hospital is better spent in getting more nurses, fewer patients per nurse, versus better diagnostic tools, for instance, right? So you can use this to help you predict that slope, especially if you make this change, what kind of impact will it have on this other variable? You can use it predictively like that as well, right? So if you have various interventions, if you want to determine whether one is more costly than the other, and if the benefit is greater than the other, then you can kind of use regression to do that. So that's the way we do this. Now, the other thing that's interesting is, I'm going to take this back up here and say, wouldn't it be interesting to see what the difference is between using our formula? We have 10 people here, we actually know what the result was. If I applied my formula here, how far off would I be for each of these 10 people? So we can go up to analyze, we can go back to correlation, to regression rather, to linear, and I can go in here and under the button save, I can click on that and I can ask it to give me the unstandardized predicted values and something called the unstandardized residuals. I'm going to click continue. I'm going to click OK. It's going to do the same analysis, of course, that it did before, but this time it did another analysis, added another analysis. And the real results of this analysis are back in the data sheet. And what it did was it created two new variables, predicted and residual. And if you look at this person here, age 30, blood sugar 75, our formula would have predicted that their blood sugar was 70, so we were off by 4.6. That is the predicted value, and the residual is called the error, right? And you can actually look at these errors and determine whether they're normally distributed. And that's what you want. You want to see them kind of like just randomly distributed, these errors. You don't want to see errors real big at the bottom end and real big at the top end, right? Because that would suggest that there's a problem with that. Imagine, think of that straight line as a teeter-totter, right? So if you put something in the middle of the teeter-totter, it doesn't move the line very much. But if you pile something up at one end, it tends to move it a lot more. So you want those differences, those errors, to be random, right? So they're spread across that whole teeter-totter evenly, right? Or normally distributed over. So that's the way we would use regression. Okay. So I'm going to play a lecture that Levi did last semester on regression. And I may not go through the whole thing, but I want you to at least see part of it. Okay, so now let me just see if there's anybody online here at home. Okay, so if you guys are online at home, and there don't seem to be that many of you, I'm a little disappointed. If you guys are online at home, I take it back if I just don't see you and I'm not right. Then I'm going to play the lecture that's linked to in this weekly material, so we can get a picture of this from Levi's perspective. Mine's a little bit simpler than his, I think, but I think you'll get little technical issues here and there, or little rules involving assumptions that correlation and regression involve, and some rules regarding correlation regression. Maybe I haven't mentioned that might come up as well. And before I do that, I think this might be a good time for a presentation. What do you guys think? Right, yeah. And then we'll take a break and I'll start the video. Okay, let's find some Scotch tape here. Anybody got Scotch tape? What's that? No, I want to put it up there because I want them to get a feel for it. Let me pause recording. Okay, I'll leave it recording. You guys got tape? Yes? No one has Scotch tape. Yes? Tell you what, I'm going to find some. Next week we're going to have poster board with pens. So, Hey, let's guys, I'm going to start Levi's thing and I'll pause it and I'll come back. I'll find some. Okay. Okay, let's pause.
This conference will now be recorded.
I think she's just happening today. All right, I'm ready.
Oh, you're ready already? Okay, good. Okay, good. I'll retrieve my email and I'll get it up here. It might take a second to load. Come on. Here we go. It's starting to load now. Which email did you send it to? School of Public Health?
No, I think I sent it to Anthony.Vito. Yeah.
Okay. Okay, let's see. Yeah, it should show up in here. Probably a big file, so it takes a while to load. Hopefully it'll travel. How big a file is it? Do you know? How many megabytes? Oh, that should be okay. Shouldn't be a problem. Yeah, I'm still waiting for stuff to load. 632. So it should have been 633. Come on. Up. Nope, that's not it. Want to try it again? Send it to Tony DeVito at Gmail. TonyDevito at Gmail. No, just Tony DeVito at Gmail. Oh, I think it just showed up. I don't think you have to do that. Yep, it showed up. Okay, we're all set. All you need to do are the arrows, the left and right arrows. Okay.
Awesome. So hi everyone, my name is Vanda Chiganzo, and I'm a health coordinator for Healthy Harlem, which works with. Sure.
Maybe. That. Maybe. It's odd. Okay, we're set.
Awesome. All right, so hi, my name is Vanda Chiganzo. I'm a health coordinator, and being a part of being a health coordinator working for Healthy Harlem, and especially just because I work with the elementary school and the students there, in the beginning of after school program, which is in October, we take the BMI pacers of all the students. And then in May, when we're done with program, we take the BMI pacers of all students. So for my final assignment, I decided to take the BMI pacers of, well, take the heights, because BMI pacer has to do with heights and weight. I just decided to take the heights of all the second grade students that I have. And basically my question was, do girls grow fast? No, do girls grow taller than boys at a young age? So, yes.
Corner there. Oh. Is that working? No, it's not working. Hang on. Okay, you got to click on that side.
Okay. So again, working as a health coordinator, this is what I decided to do. I wanted to see if the female student population grew taller than the male student population in our second grade class. So again, October marks the beginning and May marks the end of after school program. And I decided to choose the second grade students due to the fact that my ideal population, my target population would have been just young, not necessarily students, but just young people from the age of 6 to 8 years old, and have quote unquote medically well, meaning no diagnosis of diseases, no asthma, no anything. And also, if you want to get enrolled into after school program, you have to give in an updated medical and physical exam. So that's how I distinguished, okay, these are the students that are healthy, these are the students that are not healthy. So I'm just going to read this really quickly. So students had to give in a recently updated physical or other medical records before getting accepted into the after-school program. And before I took any of the students' height measurements, I asked them to take up their shoes because the soles of the shoes could give them a couple of centimeters of height. And what I utilized was a stadiometer. Does anybody know what a stadiometer is? It's like a board like this, and then like you lift it up, and then you go underneath, and then you put it on your head, and then you have to like stand straight. And this is very important because usually when you take a measurement of height, people just stand up straight like this, and you're supposed to like lower your chin a little bit and put a paper up to the ear so it's like leveled, and you're supposed to be measuring from the top, like the crown of your head, not necessarily the top part of your head. So I asked students just to lower their chin a little bit. What else? And also your calves and your butts are supposed to be touching the board. A lot of the times, because they're elementary school students, they're always like shifty and shaking, and like not like they might lean like this, and it's like no, you have to stand up straight. So it was not necessarily frustrating, but it was just a lot with the whole class of second graders. So after each student would step onto the stadiometer, I would ask them to lower their chin just to make sure everything is accurate. And again, so I decided to choose the second grade students, which is 13 students in total. Then I was thinking about it, I was like, you know what, there's actually more of one gender than the other. So out of this class of 13, I'm gonna take 5 that's male and 5 that's female, just so I can even it out, and also that could be my like population sample. So yes, so as you can see, I didn't want to put the laws, I didn't put all their names, but I did put their initials. I listed them by numbers, and then I put male or female on the side, and then this is their height measurements taken in centimeters. And then when I went to SPSS, I put this data into SPSS, and then I ran a test, descriptive frequency test, and this is the numbers that came out. So basically, for the whole class of 13 second graders, this is the maximum, this is the minimum, and I'm just going to go by the mean. So the statistic is 129.76. 77, let's say. So basically, the whole class, like that's their average of height. So then, and also just to make a distinguishing, this is in October, and then the next one, the next measurement that was taken in May. And then in May, the statistic is 131. So, hold on, 129 minus 1. Okay, so that's approximately 2 centimeters difference in height. But again, it's from October to May. So October, November, December, January, February, March, April, May. So this is like in 7 months. They grew, I would say, approximately 2 centimeters. All right, so then out of that 13, I decided to choose 5. So these are the 5 female students. This is their height in October, this is their height in May, and then I ran a descriptive test again, and then this statistic is for, this is for October for females, right? Yeah, and then this is for May for females. There's like a big, not too much of a big difference, but there's a little difference. Thought that was interesting. And then this is the Bayesian one sample statistic output box that came out when I ran that test on SPSS. I'm sorry. And then I wanted to explore the statistics as well. So this is only for the female students taken in the month of May. This is just for the month of May. And basically, I was looking at this actually the most. So the highest, the top 2 highest, I'm assuming, students that I took measurements of, these are their values, and these are the lowest students. So it's interesting to see this because even though I'm comparing female to male, it's interesting to know the difference between like the females amongst themselves and the males amongst themselves. Maybe let's say there's females that they grow taller than boys. However, a lot of the boys, they're like plateau, I guess. Like for example, let's say there's 5 guys and like their height is like 140 centimeters, all of them like together. And for females, let's say it's 145. However, there's more variation in the female population versus the male. So even though that has nothing to do with what I was looking for, I thought that was really interesting. Okay, and then this is information for October. So the highest, the top two highest and the top, like the bottom two lowest heights are there. And I thought, again, I thought that was interesting. And I just going back, I feel like there's more of a difference between, if I'm not mistaken, these numbers and the other one in May than there was in October. Yeah. Okay, so the sampling frame basically is a sample population of males now. Now we're talking about males. So the statistic, so the mean that I'm going to be using is 128. And for females, I use, what was it, 129? Hold on one second. For females, it was 132. And for males, it was 128. So if I'm comparing the sample means to prove which one is more or which one is less versus, difference, I would say that the females grew taller than the males just because based on the statistic that I'm using, which is the mean. Okay. Again, this is another test that I ran, but this is for the male students that I have. And then again, over here, I was looking at these statistics, these numbers over here. And basically, same thing. Okay, discussion. So basically, when I was looking at these numbers, I did know that, there's a wife tale that girls grow taller than guys or develop faster, quicker than guys. But I did notice, again, like when you compare the male students inside that classroom and amongst each other versus male versus female. So I'm just going to read a little bit over here. Since this is an observational study, there was no intervention to be made. I did conduct a cross-sectional study where I took the height measurements of second grade students at a snapshot in time, so October and in May. This can be observed, again, October and May. One way I conducted a retrospective study in this observation was having a component of my recruitment of second grade students being based on their health status. Again, going through their medical files, checking, okay, does this kid have asthma? Does this kid not have asthma? Do they have any kind of diseases that's listed in their medical records? And I made sure that all the students did not have anything. They were, I don't want to say healthy, because healthy, again, is like not the absence of disease, but, they were, quote unquote, medically healthy. And I would consider all the students in my observational study as cohorts, since I followed these second grade students from the month of October until the second measurement that was taken in the month of May. So that is, sorry.
Go back 2 slides. Go ahead, you finish up and we go back. Go back another slide.
One more.
Another one.
One more.
Another one.
One more.
Stop that. Okay, go ahead.
Okay.
Finish it.
And that's it. So pretty much after I took my second observation, this was, I believe, May 3rd. This was May 3rd. This was a Friday. So after I took the heights of all the second grade students for, again, the second time in May, that's when I realized, okay, so again, girls, they grew taller than guys, than the male students.
Okay, thank you.
Thank you.
Okay. I was wrong when I made that argument. I did that at 3 in the morning. So next week, I'm telling you, I'm going to have a hook here. 3 or 5 minutes. That's so we're going to practice. Practice for 3 or 5 minutes. We'll never get out of here. A great observational statistics, a great survey for the observational statistics. Would have been nice again for a graph. Because the graph makes you see things so dramatically. I would play for you guys that video from the TED Talk, that professor from Scandinavia that does this whole thing about the moving graph or the bubble and so on and so forth, with a family size and mortality and so on. Right, Hans Rosling, right, exactly. Hans Rosling, yeah. So this would have been one of the things you might have been able to do in SPSS. If you have 3 columns, and the first column, each row represents a student. First column is male or female, 1 or 2 female. Second column is their weight before and their weight after, right? You can do a paired t-test. In other words, it will automatically calculate the difference between before and after, right? And you can break that up into two groups. I'll show you on SPSS where that hides. So I still got SPSS open. So you can go into Analyze, Compare Means, Paired Samples t-test. And what you would do is you would put in the pair before and after. Let's see. I don't have data I can put in there. I'll tell you what, I'll email you, okay? So we'll figure a way to do that so that you can compare what the difference in growth was over there and see if it's significantly different for females growing faster than males or if the growth rates are equal or something. If you can show statistically with that small sample whether there's a significant difference in the mean increase in height over that period of time. Okay, yeah, and even you could also even just do the math and subtract one from the other and just have the difference in height, and then male and female, and just do a regular t-test on that as well. Okay, all right. So let me get to that. Very good. Thank you very much. No, you don't have to do this next week. You don't even have to show up if you don't want to next week. Okay, I would prefer you did because then you would get a chance to see everybody else's presentation also. Okay. Anybody else? The more we do this week, the quicker we get out next week. Okay, so let me go back to this slideshow. That's yours.
I have a question.
Yes.
In that presentation, I showed one of these graphs, the long likelihood function prior to solution. Does that have to do, because it is a graph that's linear, does that have to do a little bit with?
I'll have to take a look at it. I'm not sure. Yeah, I'm not sure where that came up, how that popped up. Okay, here's a couple of examples of scatter plots. These are ones that I believe I just went through. Strong relationship, they're clustered together. Weak relationships, they're spread out. They don't fit that line as closely. No relationship at all, it just looks like a cloud, or there is no change in one with change in the other. Okay, so, and let's see, here's a couple of numerical variables that Levi's using as an example. Under 5 mortality rates and the percentage of immunization within a population. So each one of these must represent a country, right? And so for instance, that represents a country where the immunization rate is, looks like about 32%, and the infant mortality rate, or the under 5 mortality rate is 118, right? So way up there, and we're actually probably going to be, let's see, this looks like about 184, that's probably Cambodia, that one. And each one of these dots represents a different country. The x-axis represents the percentage of immunization, and the y-axis represents the mortality rate in that country. And you'll notice as you get up towards this end, very high immunization rates, you have much lower mortality rates. So this is a strong negative correlation. The higher percentage of immunization, the lower the under 5 mortality rate. I think just when I stopped and we were starting to mention that we use the same terminology we use here as we do in all the other statistics that we work with when we're talking about the statistic that represents correlation. We call it R, or Pearson's R correlation. When we talk about the population correlation coefficient, then it's rho. Okay? We never really know what rho is. R is really our best approximation of what it might ever be. This is a more accurate version of how we determine how we get that line to fit properly and calculate that correlation coefficient. And basically it's looking at how much variability you have in the X and in the Y for each individual sample for each individual person in that sample. Okay. And again, these are the various outcomes you might get. Okay, now a couple of properties. It's a unitless number. It doesn't have any units to it. It's just simply a number. Always being -1 and +1, closer to -1, stronger than negative linear relationship, closer to 1, stronger to positive, and the closer to 0, the weaker linear relationship. Okay. So unless it's a row, the population correlation is ±1, a high correlation doesn't necessarily imply a linear relationship. In other words, it could be a non-linear relationship also. There's ways that we would look at that as well. We're getting a little bit outside ahead of what we do here. High correlation, positive, negative, does imply a causal relationship. I'm going to show you something interesting when I get through these quickly. Okay, null hypothesis, rho is equal to 0 or rho is not equal to 0. In other words, there is no correlation. There's a null hypothesis and an alternative hypothesis. A correlation exists. Notice, and I've noticed this occasionally, you guys fall back, we're not saying that R is equal to 0 in our null hypothesis. We always use the population term in the hypothesis. In other words, mu is equal to something. Mu1 is equal to mu2, not x bar is equal to. So just like that here, our null hypothesis is rho is equal to 0, or rho is not equal to 0, not R is equal to 0, and R is not equal to 0. You know, if you do it, it's not a big deal, but it's more proper to use the make sure you don't mix up the population and the sample terms. Okay, regression analysis. Okay, so now in a regression, we're looking for an association, a correlation, where the relationship is causal. In other words, one impacts what the other is. There's a dependent variable and there's an independent variable. The dependent variable is the one that is affected by the independent, or driven by the independent variable. In other words, the dependent variable is y, or f of x, and the independent variable is the x. The x determines what the y is, not the other way around. Okay, simple linear regression is only one independent variable. Now, there is a version of this that we're not going to discuss, which is called multiple regression, multiple linear regression. And in that, you can actually add more independent variables. In other words, let's say that our independent variable is age, predicting our dependent variable, which was blood sugar. Well, now maybe you can also add BMI to that as another variable, right? So you can have age as your first variable plus, in other words, beta1 times the age plus beta2 times BMI. So now maybe by comparing those, we get a line that fits better and is more predictive. That's called multiple linear regression. We're not worried about that for now. Okay, there's also a version of this that's called logistic regression, where we look at, instead of a numerical outcome, we look at a proportion or a probability. What's the probability of being diabetic? What's given that you are a certain age, that your BMI is a certain amount, so on and so forth. So you can have the probability of being diabetic is equal to, and then have these various factors. That's called logistic regression, right? Because probability of being diabetic is diabetic or not diabetic, right? So it's a logical conclusion. You are or you're not. Okay, so here's the typical linear regression formula. Beta 0 is the y-intercept. Sometimes you'll see that as alpha. Plus beta 1x is the slope. The one in front of the x is always going to be the slope. The other one's always going to be the constant or the y-intercept. And then that last term over there is the residual, or in the terms of this formula, it's a random error. It's how much you're randomly likely to miss the actual value by. Okay, and you want that to be as small as possible. Okay, but normally we're not playing with that because that's actually not part of our formula. Okay, so here it is written a little bit more neatly. Okay, and this is the method of fitting that line, the least squares. In other words, getting it so that the differences are the smallest, they balance on either side, and they are the smallest possible total value for all of these squared distances from the point to the line. Okay, I'm not going to get into this. That analysis of variance that you looked at there analyzes how much variability there is on both sides and so on and so forth to predict what the probability of there being an association or not. In other words, your p-value that you would use. Okay, remember I mentioned to you that value r squared? Okay, r squared, r squared comes up two ways. This is one, r squared is really the sum of squares of the values explained by the regression over the total sum of squares, total variability, the variability explained by the regression, the formula, over the total variability. That's called r, that's called r squared. And those are the sum of squares that we're just looking at. Another way of finding r squared is to just calculate r, the Pearson's correlation, and square it. You guys remember what it was for the example that we used? I think it was 0.81, right? 0.81. And when we squared it, we got 0.64 or something like that, right? R was 0.81. R squared was 0.64. Now, if you look at this version of calculating or path to r squared, it's a little bit more descriptive, isn't it? It says that that value is the sum of squares explained by the regression over the total sum of squares. In other words, it's the variability, the difference between the value that is that the individual really is and what the formula, how well the formula predicts it. In other words, that 0.64, the r squared, tells us that 64% of the variability in blood sugar is caused by age. That's a lot. That means only 36% is caused by other factors. On the other hand, you might get a result where it's a statistically significant result, right? And your R comes out to be 0.3, right? So what is R squared in that case? Well, 0.3 times 0.3 is 0.09, right? It's only 9%, right? Even though it may be statistically significant to 0.001, it's such a loose correlation that it only explains 10% of the variability in the relationship that you're looking for. Well, that means that it's not going to be all that predictive for you. That also tells you that there are other things out there that are determining what the blood sugar is. Besides, for instance, it was the one that, for age, R had come out to be what I said was 0.3 or something like that. If R had come out to be 0.3 and then 0.09 for R squared, then we would say to ourselves, well, you know, it's not, even though it's statistically significant, it's not such a good predictor of blood sugar. Right? Remember, my numbers were bogus. Don't think that that age is that good a predictor of blood sugar. Okay, so there's R squared. Assumptions, linearity, population regression line is straight. You can have relationships that are not linear. There might be logarithmic, right? As one goes up, it may curve up and accelerate. It may be exponential, right? The relationship between one numerical variable and another numerical variable. It happens all the time. Well, does that mean you can't use linear correlation and linear regression? Well, in a sense, yes, you can't use it just normally, but sometimes you can change it into a linear relationship. So for instance, if you have an exponential relationship, if you take the logarithms of both sides of that equation, it turns into a straight line, right? So you can change the formula to become a linear relationship. Right? Okay, so sometimes you can still work with it, but the assumption is that whatever you're working with, the values, in other words, the log of this value and the log of that value are now in a linear relationship.